Hi, welcome to this lecture on flaws in Wi-Fi protected setup, or WPS. Now, in a previous lecture, we looked at flaws in WEP and some of the design choices and the cryptographic errors that cause that to be broken. This lecture, we're going to look at a newer security model for wireless called Wi-Fi protected setup and look at a flaw in one of the designs of it and how that can be exploited in order to, again, break into a router. So let's do an intro to Wi-Fi protected setup, or WPS. Now, Wi-Fi protected setup is an optional security standard for Wi-Fi that's used to make security easier to configure for home users. And it has its own kind of fancy logo here, which is this little set of two arrows that you can see here. If you go look on your home router, chances are pretty high that there's some button or some indication of this logo on it. And in WPS, the AP is configured in WPA2 pre-shared key mode, or maybe WPA pre-shared key mode, but we'll go with WPA2 here. And the client authenticates to the AP in a different way, separate from WPA2, in order to learn the pre-shared key. So it's not meant to provide the security for encrypting packets. It's meant to provide a way for clients to authenticate to the router in order to get the pre-shared key that they would use to then connect and encrypt packets. So it's a separate layer. It's not used to encrypt packets. It's used to provide the password to connect to the router. And there are three different WPS authentication methods, three different ways that they designed for a client to authenticate to a router. The first is called push button connect. And on push button connect, there's a button on the access point. Sometimes it's on the back, and so you'll have a little button here. You can see the logo telling you what it is. And sometimes it's on the front. Again, it's a button with that same WPS logo on it. And the way that push button connect works is that when you push the button, one client can automatically connect and learn the pre-shared key. So you push the button once, and then you go to the machine you want to connect to the network, and you go to log, and you choose the network. And if your machine supports WPS, it should just log in immediately. So the button serves as a way to authenticate just one person. So you push the button, first person who tries to connect is allowed to connect and learns the pre-shared key that was chosen. It's commonly used, and it's easy to use because it's pretty simple. You tell somebody, well, if you want to connect your new laptop, push the button, and then on the laptop, click connect, and you're done. And given the use case, which is a home user adding devices or guests to their home network, it's reasonably secure in that specific scenario. Now, you wouldn't want to use this in a big enterprise environment or something because there's too many clients and you could get pretty serious issues. But for a simple home user, this is a reasonably secure solution. I mean, it's not perfect. You can come up with obvious flaws like, well, what if after you push the button, a malicious attacker connects first? Yeah, that could happen. But on your normal home network, is there a malicious attacker just waiting for you to push the button? Probably not, because how frequently are you going to push this button? Not very frequently, only when you need to add a new device. So for a home user, this is probably reasonably secure. Now, the second WPS authentication mode is called client PIN. And in client PIN, the client device, such as your laptop, chooses an 8-digit PIN, and then someone logs into the router and enters that PIN into the admin interface. And then the client is allowed to connect to the router and learn the pre-shared key. So basically, the client generates an 8-digit number. You go into the router, tell it the 8-digit number, and say, there's a client who generated this 8-digit number. And if they try to connect, you go ahead and let them. And then they'll connect, learn the pre-shared key, and then they're allowed to connect and authenticate to the access point. This is almost never used. And the reason for that is pretty simple, and that's this step 2 here. Someone logs into the router and enters the PIN into the admin interface. Home users really don't like to do that. They're not very good at logging into their router's admin interface. So this is not commonly used for that reason. It's just not very user-friendly. When you make people like open up a web browser, go to a local IP address, log in using an admin and password, click on the right tab to find, it's just kind of a disaster to do. So it's almost never used for that reason. It's just not user-friendly. The last type of WPS authentication is called access point PIN. And in this case, the access point has a pre-configured PIN code, and it's actually usually printed on the bottom of the router. So here, for example, is a picture of a label taken from the bottom of a router, and it just has a WPS PIN on it. You can tell it's a WPS PIN because it's got that little WPS symbol, and it's followed by an 8-digit PIN. It's usually printed there, and the client uses that PIN to connect and learn the pre-shared key. So if you wanted to connect to one of these routers on your client, you would choose the SSID for the wireless network, and you would say, I want to authenticate with WPS. And then it'll say, well, what's the PIN? You type in that 8-digit PIN, and then your client's allowed to connect and learn the pre-shared key that was set by the user in order to authenticate to the access point. So that 8-digit PIN on the bottom of the router is used to authenticate the client. Let's talk about that PIN in more detail, because that PIN is where the security issue comes up. So this 8-digit number is randomly chosen by the manufacturer of the router. And that means that every router should get a different one, because if all of the routers had the same one, this would be a stupid mechanism. So it's done at manufacturing time. As each router comes off of the assembly line, a random PIN is chosen and assigned to it and then stamped on the bottom. So even if you and your friend have the exact same model of wireless router, they'll have different WPS pins. When connected, it takes an access point about 0.25 seconds to verify that your PIN is correct. So if you're a client and you're trying to connect to the access point, if you send it the PIN in order to authenticate yourself, it takes about a quarter of a second for the access point to verify if your PIN is correct or not. And that was actually part of the design. They added enough mathematical complexity to the verification that they wanted it to be a little bit slow. So it takes 0.25 seconds or so to verify. Well, if it's an 8-digit PIN, how long would it take me to brute force? That's a good question. Well, there's 10 to the 8 possible pins, because it's only 8 digits. There's 10 different digits, and it would be 8 long. I can do 4 pins a second, because as I just said, most routers can verify a pin in about 0.25 seconds. So that would be 4 pins per second that you could potentially try. So if I take 10 to the 8 pins, I divide it by 4 pins per second, I get 289 days to try all pins, or 144.5 days on average, because on average you'll find it halfway through, right? Well, that's not bad, actually. Is it okay that someone could break my WPS pin and get into my router in 145-ish days? Yeah, that might be okay, because again, we have to think about the deployment scenario. This is home users. If my neighbor really wants to use my access point to get on the internet, and they invest 145 days of one of their computers constantly trying to brute force my PIN, yeah, they'll probably get it. How much of a threat is that? Not very much of a threat. Because that's a lot of work to use your neighbor's Wi-Fi, to spend that long trying to do that. I mean, we're talking 5 months of continuous having some computer dedicated to trying to break into your neighbor's Wi-Fi access point. It's just not something most people are going to do. But you could debate whether 145 days is reasonable or not, but for now, let's just pretend that that's reasonable. Well, there's some problems with the way this was designed and implemented, and let's talk through those. So there are some implementation issues that make this worse, 2 specifically. The first is that even though it's an 8-digit PIN, the last digit is really a checksum, and it's used to detect if the user enters the PIN wrong. So the first 7 digits of the PIN are randomly chosen by the manufacturer, and the 8th digit is calculated mathematically based on the first 7. The goal there is that if the user types in their 8-digit PIN wrong, you can just use that simple mathematical check on the 8th digit to figure out if they were, just to detect that they made a typo. But that means that even though it's an 8-digit PIN, only 7 digits are actually chosen. The 8th one is just calculated. So it's really a 7-digit PIN, which means there's really only 10 to the 7 possible pins. Well, now I have to rethink my brute force calculation, because I assumed an 8-digit PIN. If it's really only a 7-digit PIN, well, then my brute force time ends up becoming about 29 days, or 14 and a half on average. Okay, this begins to make me uncomfortable. When I say your neighbor's going to spend 5 months trying to brute force your access point, you think that's ridiculous. But when I say your neighbor's going to spend 2 weeks, you think, wow, he's dedicated. But could someone do that? Sure. Would they be willing to? Maybe. So 2 weeks doesn't make me too happy. But again, it might be okay. It might, because we're still dealing with the threat model of home users, and how many neighbors are really going to spend 2 weeks dedicated to breaking your access point? Hopefully not many. There's another problem with the PIN, though, and that is that the PIN is verified 1/2 at a time. So here's a simplified version of the PIN verification protocol, really simplified, to help you hopefully see the problem. So I have my client there on the left, my access point on the right. So the client uses an HMAC in order to do the authentication, but it basically sends an HMAC with some randomness chosen on the beginning and end, and in the middle it includes the first half of the PIN. Now the router verifies that the client did indeed know the first half of the PIN and sends back, oh, that's correct. And then the client sends the second half of the PIN in the same way, using this HMAC with some special randomly chosen values on the front end. And then if that's correct too, then the router goes, great, here's the pre-shared key so that you can connect and send your encrypted packets. But this means that the client sends the first half of the PIN, the first 4 digits, and gets feedback about whether or not that's correct before it tries the second half of the PIN. That's problematic, because that means if I'm running a brute force attack, I don't have to get all 8 or I guess 7 digits right at the same time. I can figure out the first 4 separately from the last 4. So I can brute force the first half of the PIN separate from the second half. That's very problematic, because that changes my brute force attack drastically. I can check the first half of the PIN, because now the first half is only 4 digits, in 10 to the 4 over 4, which is 41.67 minutes. So I spend about 41 minutes to get the first half of the PIN. And after I get the first half of the PIN, then I have to get the second half. Well, the second half is shorter, because remember we're dealing with a 7-digit PIN. So that's only 10 to the 3 possible second halves. If I divide that by 4, because I get 4 tries per second, then that gets me 4.17 minutes. So I spend 41 minutes getting the first half of the PIN, 4 minutes getting the second half of the PIN, for a total attack time of about 45 minutes. That's pretty bad, actually. I mean, you have to admit, when your neighbor can break into your Wi-Fi in 45 minutes, now we have a problem. So that's an issue. So these two design choices that were made for the PIN have drastically impacted its security. So the first design choice was, instead of 8 digits, it's actually 7. And the second design choice was that we would authenticate the PIN 1/2 at a time. So this is a pretty major issue. So we went from 5 months to brute force the PIN to 45 minutes. And this is the worst case, 45 minutes in the worst case. On average, we'd be able to do it in 22 minutes? Is that what we get if we do that on average? So that's a bad thing. Now there's an implementation of this attack, and it's called Reaver. If you Google for it, you'll find its website. It's a brute force attack against Wi-Fi protected setup. It's also available in Kali Linux if you wanted to play with it a little bit on your access point at home. So if you have an access point that implements WPS PIN, you can try Reaver and just see if it would work. So how do we prevent this type of attack? Well, there are two kind of groups who need to be able to handle prevention. First is users. If you're a user and you have a router, how do you prevent this attack? And the other is vendors. If you're making access points, how do you prevent this type of attack? Well, for users, the most important thing you could do, you could disable WPS on the router. And that's kind of what's been recommended. You should just disable Wi-Fi protected setup on your router. Well, this has 2 problems. The first is that most users aren't even tech savvy enough to change the time on their microwave. So they're definitely not going to be able to get into their router and find some obscure setting for WPS and turn it off. The second problem is that many routers don't even let you disable WPS. Even if you go into the admin interface, there's no option to disable it. Even worse, some routers will let you check an option to disable it, but then they won't. It doesn't work. That's the worst thing. You go in, you disable WPS, but then it's not actually turned off. So users preventing this attack, it's difficult. It's unlikely to have good widespread adoption for that. Vendors, the people who make access points, however, they have some potential options. The first and the most common one is they could try to rate limit PIN attempts. This means that instead of allowing 4 pins per second, you artificially rate limit the PIN attempts to be slower. So for example, you could say after some number of attempts, there's no more WPS authentication for Z minutes. So you could say after 3 attempts, there's no more WPS authentication for 5 minutes, for example, in order to drastically slow down the attack. And this is what a lot of access point makers are actually doing. They'll do some sort of rate limiting. So let's summarize. WPS was added to routers in order to make security easier for home users to do. And so the goal was simply to make security more attainable for home users, mainly so that they would stop setting up their access points in open mode where nothing was encrypted at all. But the WPS AP PIN method has two flaws. There's a small number of possible pins, and the PIN is verified 1/2 at a time. Now, Reaver is a tool that exploits this flaw that you could potentially experiment with. So that's kind of our summary of today. Thanks.